Operating principle of drones. Drones, also known as unmanned aerial vehicles, UAVs, are a type of aircraft that can fly without a pilot on board. Drones are automatically controlled by an onboard computer or remotely controlled by an operator. The operating principle of drones involves the harmonious integration and synchronized operation of several main subsystems to achieve stable and controlled flight. These systems include propulsion, flight control, power supply, communication, and sensors. This detailed summary explores the operating principles, mechanisms, and components that enable drones to fly and operate effectively in various environments. 1. Basic physics of drone flight. The flight principle of a drone is governed by aerodynamic laws and Newton's laws of motion. In the case of multi-rotor drones, mainly quadcopters, the main forces acting on the drone include lift force, an upward force generated when the propellers spin at high speed, counteracting the weight of the drone. Weight, gravity, a downward force caused by Earth's gravity. Thrust, a force that propels the drone in a specific direction by controlling the speed of each rotor. Drag force, air resistance acting opposite to the drone's motion. When lift and weight are equal, a stable hovering state occurs. Moving forward, backward, or sideways is achieved by tilting the drone and changing the direction of the lift force through adjusting the thrust of each motor. 2. Propulsion system. The propulsion system is very important in generating lift and controlling the drone. In a typical quadcopter, it includes brushless DC motor, BLDC, an efficient and lightweight motor that spins the propellers. Electronic speed controller, ESC, adjusts the voltage to control the speed of each motor according to commands from the flight controller. Propellers push air downward to create lift. Pairs of propellers spin in opposite directions, clockwise and counterclockwise, to balance torque and allow stable rotational control. Each motor propeller pair generates torque. According to Newton's third law, to avoid uncontrolled spinning, the propellers spin in opposite direction. 2 spin clockwise, CW, and 2 spin counterclockwise, CCW. Propeller control logic, e.g. quadcopter. Hovering. All motors spin at the same speed, ascending/descending. Speeds are increased or decreased evenly. Pitch. Forward, backward. Increased speed of rear, front motors, and decreased speed of front/rear motors. Roll, left-right. Increased speed of right-left motors and decreased speed of motors on the opposite side. Yaw, rotate left-right. Increased speed of clockwise spinning motors and decreased speed of counterclockwise spinning motors, or vice versa. 3. Flight control system. The flight controller, FC, is the central processor of the drone. It decodes signals from the remote control and the sensors on the device to adjust the motor speed through the ESC. The main components include microcontroller unit, MCU, runs control algorithms and sensor fusion. IMU, inertial measurement unit, includes accelerometer and gyroscope to measure attitude, acceleration, and angular velocity. Barometric pressure sensor measures pressure to determine altitude. Magnetometer sensor acts as a digital compass to determine direction. GPS module provides position and velocity data from satellites. In drones equipped with GPS, Stabilization and control algorithms. The flight controller runs complex algorithms such as the PID controller, proportional integral derivative, to maintain stability. These algorithms analyze sensor data and continuously adjust motor outputs to keep the drone balanced and responsive. 4. Power system. Drones mainly use lithium polymer or LiPo batteries due to their high energy density and high discharge rate. The power system includes battery, provides power to the motors, flight controller, sensors, and payload. Power distribution board, PDB, distributes power from the battery to all components. Voltage regulator ensures sensitive electronic devices receive stable voltage. LiPo batteries are rated by voltage, number of cells, e.g. 3S 11.1V, capacity, mAh, and discharge rate, C rating. A high C rating allows for faster current output, which is important for maneuvers requiring high thrust. Communication system. Remote-controlled drones require a robust communication system between the pilot and the UAV. There are two main channels: radio frequency, RF, control transmitter, TX, a handheld device used by the pilot to send control signals. Receiver, RX, installed on the drone, receives signals and transmits them to the flight controller. Mostly operates on the 2.4 GHz band, control, and 5.8 GHz band, FPV video. Data collection, telemetry. The data collection module sends real-time information, such as battery voltage, GPS position, altitude, and speed, to the ground station or mobile device. This allows monitoring and diagnostics during flight. First-person view, FPV. To provide real-time video feedback, the FPV system includes camera mounted on the drone, video transmitter, VTX, sends real-time video signals to FPV goggles or display screens. Video receiver, VRX, placed on the ground and connected to the display system. 6. Navigation and automation. Autonomous drones rely on precise navigation systems to perform tasks without human intervention. The main components include GPS, navigation. GPS provides geographic location and speed data. It enables waypoint navigation, return to home, RTH, and geofencing. Inertial Navigation System, INS, combines data from the IMU and GPS to estimate position and orientation, especially useful when GPS signals are unavailable. Optical flow. Sensors. Cameras or laser sensors detect ground movement to maintain position or navigate indoors without GPS. Computer vision and artificial intelligence. Advanced drones use cameras and machine learning to detect and avoid obstacles, e.g., SLAM algorithms. Track and follow targets, e.g., human faces, vehicles. Recognize objects and environments. 7. Payload and auxiliary systems. Depending on the purpose, the drone can carry different types of payloads, such as camera for aerial photography and inspection, thermal sensors, LiDAR or radar systems, delivery mechanisms, environmental sensors, e.g., gas, radiation. These payloads can be stabilized by a gimbal, a mechanical platform that uses motors and sensors to isolate the camera from the drone's movements. 8. Software and control interface. Drone operation is usually managed through a software platform that allows mission planning, defining waypoints, altitude, speed, and camera movements, flight logging, recording data for analysis or regulatory compliance, adjustment and calibration, fine-tuning PID settings, sensor alignment, motor output control. The main platforms include Ardu Pilot, PX4, DJI Go, Fly App, Huge Round Control, Mission Planner. 9. Safety and backup mechanisms. Modern drones have safety features to protect the device and those around it. Backup mode automatically lands and returns to the starting point when signal is lost or battery is low. Obstacle avoidance uses ultrasonic, infrared, or image sensors. Geofencing prevents the drone from entering restricted areas. Backup systems, dual GPS, IMU, and backup power supply for critical situations. 10. Types and components of drones. The operating principle is similar depending on the type, but the implementation methods differ. Multi-rotor, the most common and easiest to control, includes quadcopters, hexacopters, and octocopters. Fixed-wing drone uses airplane-like wings to generate lift and is efficient for long flights. VTL, vertical takeoff and landing, combines features of fixed-wing and multi-rotor drones. Single-rotor helicopter uses one large rotor and a tail rotor with a complex mechanism. Nano/micro drones, miniature drones used indoors or for special purposes. Conclusion. The operating principle of a drone lies in the seamless integration of mechanical, electronic, and software systems. The propulsion system generates lift and thrust, sensors provide real-time feedback, and the flight controller decodes commands to maintain stability and direction. Whether manually or automatically controlled, a drone is a brilliant combination of various engineering fields, enabling applications from recreational flying to industrial inspection, delivery systems, and agricultural monitoring. As drone technology continues to advance, innovations in artificial intelligence, battery performance, and materials science will expand the capabilities and accessibility of drones, opening new horizons in aerial mobility and automation.